even if quantum mechanics, quantum computing sounds like science fiction, but it is moving closer and closer to reality. And there is a cyber security threat happening right now that most organizations don't even know exists. Adversaries are waiting for quantum computers to break today's encryption, which they will. Bad actors have started harvesting encrypted data that they cannot decrypt right now, but they're harvesting it because storage is cheap. They're storing it and planning to decrypt it the moment quantum computing becomes powerful enough. It is dangerous and it's called harvest now, decrypt later. And if your organization's sensitive data has a shelf life longer than 5 to 10 years, you're already at risk. So how do you protect data that is being stolen today but won't be cracked until tomorrow? That's exactly what we are going to find out in this episode of Secure by Design with Jeremy Allison, distinguished engineer at CIQ and co-creator of the Samba project that we all use. Jeremy, it's great to have you on the show.
Oh, it's great to be here. Thank you very much for inviting me.
Jeremy, let's start with the basics. Let's start with what's driving all this urgency around post-quantum cryptography. What exactly is PQC or post-quantum cryptography, and why are we talking about it now when practical quantum computers might still be years away, still kind of in the realm of science fiction?
Quantum computing, I mean, it's essentially magic. From what I can, my own opinion is using the computing power in parallel worlds to solve problems in ours. I'm not a quantum cryptographer. I'm an engineer, so I make the code that protects against it work. But essentially, the fear is that quantum computers will be able to crack our current key exchange algorithms, which are mostly based on elliptic curve and RSA. They're the mathematics. And a lot of those are to do with the factorization of large integers. Now, it turns out that one of the earliest algorithms written for quantum computers was something called Shor's algorithm, which actually focuses on factoring large integers, which is basically the problem that RSA uses to protect all of our banking, all of our medical records. So the idea is to use post-quantum algorithms, and these are algorithms that have been standardized by NIST, the US National Institute of Standards and Technology, to protect against attacks where somebody collects data now that's flowing over the internet, and they can't decrypt it, they can't do anything with it, but storage is cheap, right? Everybody's got 20 terabyte disk drives. You keep storing this stuff. And then later on, when quantum computers come online, the fear is that you can then decode all that and you can read the plain text of all the things that people were communicating at that time. And so, you know, the fear is this could happen sometime. Well, I mean, look at AI. It's happened faster than anyone expected. So the goal is by 2030 that we should have moved to post-quantum algorithms. And these are algorithms that I don't understand, got to be honest, created by mathematicians that will protect against quantum computer decryption. Now, the main protocol that everyone is concerned about is TLS, Transport Layer Security. And that's basically the web protocol. That's what we're using right now to communicate on our browsers. That's almost it's what Amazon uses when you're doing S3 or cloud computing or Google or Microsoft. They all use TLS to protect the data in transit. And so the algorithms that have been created are actually around protecting the key exchange. The bulk data encryption, usually using AES, is mostly considered safe from quantum computers. But the key exchange, if you can get the keys that are exchanged when you first make that connection, then, you know, it doesn't matter how good your encryption is after that, you know how to decrypt it. So the goal is to protect the key exchange and also the signatures. So there are two algorithms called ML-KEM and ML-DSA that are basically the post-quantum algorithms. And those are the ones that we have gotten FIPS. Well, we're in the module in process list, but our algorithms have been tested as correct, and we're getting FIPS certification for those algorithms.
You mentioned harvest now, decrypt later attacks. Walk me through what does that actually mean in practice? Are we talking about a theoretical threat, or is it actually happening right now?
Oh, I'm sure that's happening. I'm sure that's happening right now. Governments and bad actors, they're all collecting as much encrypted data over TLS as they can possibly get their hands on and storing it away in the hope that when quantum computers arrive, they can just decrypt this and read it as though people were conducting plain text conversations over the internet. It would be like, using Telnet was in the 1990s. You could basically read everything that was going over the internet. So that is going on right now. I'm absolutely sure of that. Now, so the goal is to move everybody onto the post-quantum algorithms as soon as possible. But this is going to take time. Think about all of the equipment that is deployed right now, all of the embedded systems, all of the Linux servers, everything. We need to start now to transition all those devices onto modern code bases using post-quantum algorithms to prevent, there's nothing we can do about the stuff that's already been collected using the older algorithms. But what we can do is roll this code out as soon as possible so that you can start using it as quickly as possible. And that's what the FIPS certification is about. It's basically saying, and I believe it's targeting 2030, it's saying by 2030, you must be using, especially governments and government-approved systems, you must be using these post-quantum algorithms to protect, and I'm sure banks and major corporations all will follow. Anyone who's serious about protecting their data needs to start moving to post-quantum algorithms.
What's interesting about CIQ is that you folks have achieved something pretty significant. Your NSS module for Rocky Linux has become the first to get CAVP certification from NIST for post-quantum cryptography algorithm. But you have said the algorithms were already feature complete. What is the difference between having working code and actually being FIPS compliant?
So this is... Working code is somewhat the easy part of things. There are many libraries out there that implement post-quantum algorithms. They're correct. They're done by open source engineers, people who understand this stuff. They're feature complete. You can use them. But in order to get FIPS certification, there is a step way beyond that you have to do. And so the kind of things that you have to do are, here's an example. The code I was working on was originally written in Rust, the Rust language, converted into C by an automated process. And so in that automated process, it leaves a lot of intermediate copies of data. Just the process of transpilation creates those. Those all have to be zeroed out in order to make a secure implementation. The implementation works, nothing wrong with it, but it's not certifiably secure because it doesn't zero out all of the intermediate values that are left lying around in the computer's memory. So I had to go in and basically add all of that code to the existing open source code. And we've published all this stuff. This is nothing proprietary, nothing secret. It's all published on the website, linked to by the blog post. You have to zero things out. The other thing that you have to do for FIPS certification is when the library is first loaded, you have to run tests that say, yes, I ran this algorithm through a certain test vector, and it created the correct output. And in some cases, you have to say, and I corrupted the input test vector, and I made sure I got a different wrong output. So all of that code, this is the unglamorous part of making these algorithms. This is the FIPS certification part. So actually writing the algorithms and having it all work, that's the fun, sexy part, right? Making sure that you actually run these tests, and they're called CATs, known answer test. And then when you generate keys, you have something called pairwise consistency tests. All of these things need to be added into the code. And usually what happens is they're the last thing, because they're the boring part. They're the part that nobody wants to work on. So they're the last thing to get added. And in this case, they were just missing. Some of them were missing. So we had to add those. And again, we've submitted all this stuff upstream. And this is what we have to do for all of the libraries we work on. But this was the first library that we worked on that had the post-quantum algorithms ready for certification. There are more coming. There will be many more libraries that we're tracking in open source. This is why a lot of the open source libraries, they don't really care about FIPS. It's not their target market. They want to get the code working. They want to get the algorithms out there. They want to get it widely used. Making it certified by government is very low on their priority list. And so basically that's where CIQ and other vendors come in and actually do that work. Because it's not the fun, exciting stuff, but it's essential work that has to be done if you're able to go through the certification process and get your certificates that say, yes, this is correctly implemented, it's tested, you can deploy this safely.
While I do understand that open source community or open source developers, they don't have that much time. Mostly they work in their free time. They volunteer to all these projects. But now we have laws like CRA, where we cannot have the luxury of not caring about code and security. So what impact can CRA have on these kind of projects?
Oh, yeah. It's not fair to expect the open source projects to do all this work for free. The maintain a burnout problem is hard. The fact that everyone's seen that XKCD cartoon of comic of the entire internet infrastructure and one guy working on his own in Nebraska who's holding everything up, who's implementing this essential piece. That's really kind of true. You can't expect open source projects to care about the details of FIPS certification. That really is for the people who want to take that code and deploy it. They're the ones who have to basically go through the standardization processes and make sure everything works. Now, obviously you can, we submit that stuff upstream, we make it available. We don't want to keep anything proprietary around this, but the hard part is actually going through the certification process, because it's a very involved process involving collaboration with a government lab, lots of back and forth, code reviews, bug reports, fixing bug reports. It's quite a long process, which is why we're so pleased to get there.
Here is what I'm curious about. You are tracking PQC implementation across 5 different FIPS cryptographic modules. Why is it so complex? Why can't you just flip a switch and make everything quantum resistant?
Well, so why is it so complicated? These are implementations that have to modify the TLS key exchange protocols. And that's actually, somebody worked out that if you printed out the TLS specification, it would be several feet high worth of documents. And the idea is that there are different ways of doing this. You can do what's called hybrid post-quantum, where you mix the post-quantum algorithms in with existing algorithms. So essentially you're getting the best of both worlds. Or in the future, they may standardize on just quantum resistant only. And this very much depends on how mathematicians, or whether mathematicians are able to crack the post-quantum algorithms. And this is an area well beyond my area of expertise. I just watch the mathematicians and the papers come out and, look at the recommendations coming out from the IETF. But it's difficult and it's complicated because you have to mix this into existing protocols in a way that existing devices that don't use these things still work, and yet modern devices that have post-quantum can recognize each other securely and say, oh, you want to use post-quantum, I want to use post-quantum, let's do that. And you have to do that without what's called a man-in-the-middle downgrade attack, where someone sits in the middle and says, hey, I'm pretending to be the other side to each other, and I'm going to force you to downgrade to a non-post-quantum algorithm so that I can collect and decrypt later. So it's actually quite a complicated process. And of course, you have to test all of this. And this being open source, there are 5 different implementations of the same thing. Some projects use one, some projects use another. And so in order to be really secure, you have to make sure that each of those has post-quantum algorithms implemented in them. And, NSS is just the first. I think the next one, and they're already very well ahead of this, is OpenSSL. Probably GNU TLS will come along a little later. I'm still tracking that. I monitor upstream very carefully to see what's coming down the line there. And then the Linux kernel, well, the Linux kernel is the Linux kernel. That depends on the taste of Linus, and he doesn't like FIPS very much. Because security gets in the way of what he wants to do. So, that will be done probably by the security team, the people who maintain the crypto code in the Linux kernel. We'll have great faith in them. So, but they're not there yet.
Who actually needs to care about it right now? What industries are most at risk from these harvest now, decrypt later attacks? And what do compliance regulations actually look like for PQC today?
Everybody should be thinking about it. even the people who are just doing the routers that sit in people's houses should be thinking about this. Essentially, obviously defense, finance, healthcare, people who are really going to get fined big time if they have data breaches. Obviously, they're the ones who need to consider this first. But eventually, it's going to affect everybody. My big fear is the Internet of Things devices, where you have these, $20 devices that use TLS. They're never going to get fixed. No one's ever going to upgrade the code on those. So they have to get replaced, and a security is only as strong as its weakest link. So, everybody has to start thinking about this, but it's very hard to move the entire industry forward on secure communications, But I mean, the whole point is to move everybody as fast as we possibly can to the highest level of security, appropriate for what they're doing, of course. But anyone who's dealing with customer data really has to care about this.
You are dealing with 2 different algorithms here, ML-KEM and ML-DSA. Break those down for us. What do they actually do, and why do we need them both?
Well, KEM is the key exchange algorithm. So that really is the one. When you are first setting up a TLS communication, you need to exchange keys so that each side has a common encryption key that they can then use for bulk encryption. And so that's where ML-KEM comes in. The ML-DSA algorithm is used for digital signatures, where you have data that you have to verify, you have to sign, and you have to be able to verify that this comes from the person who had this particular private key. And so they're the 2 different uses, but you do need both. It's not quite accurate, but sort of the data in transit is ML-KEM, data at rest is more the DSA algorithm is probably the simplest way to look at it. It's not completely accurate, but...
Now, another achievement for Rocket Linux is that you folks are the first enterprise Linux distribution advancing towards full FIPS 148-3 validation for PQC. What makes this validation process so brutal for open source projects, and why isn't the upstream community just doing this work themselves?
Well, I mean, open source projects are not going to do this because it's expensive. Because you can have all the best code in the world, or I mean, all of the code that we've got is all open source, and yet you have to go through the lab. The lab has to test this stuff. The lab has to write up your security policies. This costs a lot of money. Open source projects are not going to do it, and you can't expect them to. It's not really their role. The major vendors, they all have FIPS certifications to some extent. I think this is the first post-quantum one. I'm sure everyone else is eventually going to do this. It's nice to be first. And of course, I would recommend people look at CIQ, CIQ's Rocky Linux. But yeah, it's a matter of going through the process, and the process is expensive, long, and very, very detailed. Very detailed. Because they have, as I said, they have to examine all of the code. And you have to work with them on feedback, you have to propose patches, they have to agree with them, all the algorithms have to be tested. It's a detailed process, because essentially the labs are putting their reputation on the line. They're saying, we guarantee that if you use this code, you are using correct algorithms, correctly implemented and tested. So they can't make a mistake. They put their reputation at risk if they make mistakes. And so it's a difficult process, I'm not saying whether, everyone else is doing this too. I'm just happy that we got our NSS done with PQC first. I'm sure others will follow.
Let's get practical. You are expecting full FIPS 140-3 validation for NSS in second quarter of 2027. OpenSSL validation is starting later this year. What should companies be doing right now to be fully prepared? What does a realistic migration path looks like?
You need to start turning off older algorithms. So this is a security policy. This is a security policy kind of thing. So you have to start looking at the applications that your business depends on and the libraries that they depend on, and you have to conduct an audit of what algorithms these libraries are using and whether those algorithms are going to be FIPS compliant and also post-quantum secure. And you have to start turning off the algorithms that are not. And as soon as you do that, of course, everything will break. Lots of applications that people are using will break. I mean, just some of the storage. I think iSCSI, the standard algorithm, I'm originally a storage engineer, obviously, from Samba. The original iSCSI storage algorithm, security algorithm, is completely deprecated now. Shouldn't be used anymore. So, sometimes you have to say, okay, well, we can't really use that protocol anymore. We have to migrate to a more modern one, or we have to rev the standards so that you can put stronger levels of encryption, more modern algorithms in there. I mean, look at Microsoft and how long it's taken them to get rid of NTLM, which was the authentication algorithm used in the original Windows. They're only just getting rid of that now in Active Directory. So it takes a long time, especially the larger your deployed user base is, the longer time it will take to migrate. But you need to start looking now, and at least in your test labs, you need to start turning off algorithms and saying, does my stuff still work if I turn this off? And so that's kind of how you need to start approaching it. But in order to do that, you first need a secure audit of what am I actually using? Because you can't fix things that you don't know you have. So getting a full audit of the software bill of materials that you're using. Everybody uses open source code. everybody uses open source code. It used to be that you went Microsoft, you could say, no, I'm only using Microsoft stuff. But these days, Microsoft uses open source code. So you need to know what it is that you have in your organization, what algorithms are being used, and create a migration plan to move to a more modern, more secure future.
The NSA's CNSA 2.0 sets transition milestones starting in 2027 with full migration by 2035. That sounds like a long runway, but you are saying organizations need to act now. Why is this urgency, and how the people who are watching this discussion should start preparing right now? What is your advice to them?
We stand on the shoulders of giants. We've taken open source code, worked with it, passed it through the certification. Other people can do the same. Hopefully other people will take the code that we've published and do the same for them. We're hoping to move the whole industry forward. I think we're great, but there's nothing special about what we do. Many people can do it, especially as the code is public. You can take it, you can examine it. So at least, even if you're not going through the lab certification yourself and you don't need to have a certified product, you can still use the same code that has been certified, because it's freely available to you. And so, if you take anything away from this, it's please learn from other people. Use other people's work. They've made it freely available for you. It's there for the taking, and it will help make your environment, your industry, your company more secure. And that's the goal that we all want. Obviously I'd love it if you bought it from us, but I'm an engineer, not a salesperson. You go to CIQ.com. I'm sure they'll happily point you at the right salespeople for whatever it is you want to buy. But I as an engineer, I would like to move the whole industry forward to a more secure post-quantum future.
Jeremy, thank you so much for joining me and breaking down post-quantum cryptography and what organizations need to be thinking about. Right now, the shift to quantum-resistant infrastructure is coming faster than most people realize, and I look forward to another discussion. Thank you so much.
Oh, thanks so much for having me on. It's been a lot of fun. I really enjoyed our discussion, and I hope it's been useful for your viewers.
And for those watching, if you are running infrastructure that needs to be secure 5 or 10 years from now, make sure to check out CIQ and Rocky Linux, and don't forget to subscribe to TFIR, like this video, and share it with the team. Thanks for watching.